Well, we're back here at the Cave of Science, and we're looking at the assessment review from the EM spectrum. And this is going to be the same thing we did in class for those that want to do the retake. Now, one thing to remember, this is reviewing this assessment. The retake assessment will be similar, but won't be exactly the same. First one, why can you see light from the sun, but not hear the sun? Well, an EM wave can move through a vacuum. Oops. Which like a vacuum, I think I spelled that wrong, or move through V-A-C-U-U, move through a vacuum, or the emptiness of space. Sound needs a medium, or something to go through. So that's the big difference there. In this particular next question, determine the wavelength of a microwave. Well, if it's a microwave right away, we know it's an EM wave. So we know the formula is going to be frequency, the speed of light, times frequency times wavelength. We know the speed of light is 3 times 10 to the 8th meters per second. We know the frequency is right here, 3 times 10 to the 9th hertz. We don't know the wavelength, so that's what we got to solve for. So C, 3 times 10 to the 8th meters per second, equals frequency, 3 times 10 to the 9th hertz, and we got to solve for the wavelength. So we're going to divide each side by 3 times 10 to the 9th hertz. And at this point, if you don't put the units in, that's fine, because wavelength is in meters. 3 times 10 to the 9th hertz. And as you go ahead and do the math on that, that's going to be 0.1 meters. And if I did that on my calculator, so 3e to the 8th divided by 3e to the 9th equals 0.1. And that's as simple as that. Question 3, relate wavelength, frequency, and energy of a microwave to that of an X-ray. So I got a micro and I got an X-ray. Well, if we're going to look at the two, microwaves have a lower frequency than that of an X-ray. So these are going to have a lower frequency, so they're going to have a longer wavelength, and they're going to have low energy. An X-ray, on the other hand, has high frequency, so it's going to have a short wavelength, and it's going to have a high energy. So for really, when you think about any electromagnetic wave, the higher the frequency, the shorter the wavelength, the higher the energy. A distant star has a wavelength of 4.7 times 10 to the 7th meters. What is the frequency? Again, it's light, so we're going to be using frequency times wavelength. So we know C is 3 times 10 to the 8th meters per second. We don't know the frequency, but we do know the wavelength. 4.7 times 10 to the minus 7th meters. I'm not going to put the units when I do this one, but frequency, you know, is measured in hertz. So 3 times 10 to the 8th equals, we don't know the frequency, but we do know the wavelength. 4.7 times 10 to the minus 7. So divide each side by 4.7 times 10 to the minus 7. 4.7 times 10 to the minus 7 4.7 times 10 to the minus 7. And let's see, I guess I'll do it on my calculator here. Let's clear that one out. So 3e to the 8th divided by 4.7 e, and that's in the minus 7th, so you got to do the change of sign key down here. And that's to the 7th. And just hit enter. And 6.4 times 10 to the 14th. So this is going to equal, frequency can equal question number 5. There's our Snell's law. And the formula is given to you. It's index refraction of 1 sine theta 1 sine theta 2. Well, if we look at this, make our table. N1 equals 1.5. N2 we don't know. Here's our first angle. The sine of 45 is 0.71. So I can say sine theta 1 equals 0.71. Sine theta 2 equals 65. And that's 90, or 0.90. And now we'll just plug in. N1 is 1.5. Don't know N2, sine 2 is 0.90. Well, find the answer. Multiply these two and divide by this. So 1.5 times 0.71 equals now about 1.07. So 1.07 equals N2 times 0.90. Now I very simply divide each side by 0.90. 0.90. This is gone. So 1 point, I'm just going to leave that because I already have it up there. Divided by 0.9 equals 1.18. So N2 equals 1.18. That's all that one is. Problem 6. Describe 2 ways you can reduce the intensity of light reaching a surface. This is what we did in your QPO. 1, you want to reduce the intensity. Move light farther away. Or increase distance between the light and the observer. Number 2, decrease the angle the light strikes the surface. Decrease angle light strikes surface. And if you remember, you did the lab, you had the light at 90 degrees straight overhead shining down, and then you kept decreasing the light hitting the surface, and it kept making a bigger and bigger circle. Well, you didn't change the intensity of the light. It still gave out as much light as it did strictly overhead, but it covers a bigger area, so mathematically the intensity will go down. Number 7, waves on a string. Well, right away it's telling you it's got to be transverse, and that's what you did in there. And if it's not electromagnetic, because you didn't work with light, it's got to be mechanical. Because you didn't squeeze a piece of string together. And the parts of the wave, label that. point to point here is wavelength. This would be trough. This is the crest up here. And this distance from the line of origin to the crest, or the line of origin to the trough, that's amplitude. Could be that or that. Is low reflectivity. It is true also. High reflectivity is low absorption. Number 9, 2. So we'll put number 1 here. Let's put number 2 over here. This is the Doppler effect. So observer 2, as the object's moving away, it's racing away from its own wavelength. So we have long wavelength, so we're going to have low frequency. For observer 2, it's catching up to its own wavelength, so we're going to have short wavelength. And we're going to have high frequency. And that's all that question's asking for. This one, very simply, the angle of reflection. Those two angles are equal. So that was this assessment. The next assessment will be similar, but not exactly the same. So I would definitely use the same review sheet, and that's where that's going to be. Alrighty. We'll see you later.